Okay, very good. So, thank you for this super nice introduction round. I am so happy to be here as a guest speaker at Rostock. My name is Rainer Stropik. I already introduced me. I'm a passionate developer for nearly 30 years now. I started my programming career with C and C++. Well, honestly, my very first programming steps have been in BASIC and Pascal, but then professionally I started development with C and C++. Then I discovered C# and .NET at the very early stages of these platforms. Then I also added a lot of Node.js, TypeScript, JavaScript development to my tool belt. And over the years, I also added Go. And in the last few years, Rust became a super important part of my technology stack, of the technology stack that I typically work with. And this is, I think, the reason why you asked me to come and do a talk here at the Rostock meetup. Today's talk will be about WebAssembly. And I've done quite a lot of WebAssembly talks in the past few weeks and months. And if you have seen some of them, you know that I'm a big fan of WebAssembly. I really think that WebAssembly is a game changer in many areas. Of course, in front-end development, because we can use languages other than JavaScript to write software for the browser. But I personally am even more enthusiastic about WebAssembly on the server, so outside the browser, using WebAssembly to build kind of microservice applications and architectures that are no longer microservices, because we can mix and match different programming languages and runtimes in one and the same WebAssembly module and so on. However, today will be a different talk. Today, I will not show you things about fancy rendering stuff in the browser. I will not spin up Spin or something like this to start a web server in Wasm. Today, I prepared a little different I prepared a talk for you that is a little bit different. I would like to really take a look at the fundamentals of WebAssembly. What is WebAssembly? How does WebAssembly work behind the scenes? How does WebAssembly look on a binary level? How can we write WebAssembly code without any programming language except just WebAssembly? And the next step, what we'll do then is we will try to mix in Rust. So we will try to write a little bit of Rust. And when we got this Rust code, we will compare the WebAssembly code that will be generated by the Rust compiler. And we will try to find out interesting things about what Rust adds to WebAssembly in order to make it work. And the third step will be even one step further. We will take a look at Wasm bindgen and try to find out why Wasm bindgen and Wasm pack and tools like that are super useful, but also what their drawbacks are compared to native WebAssembly. So we will really build a solid foundation of WebAssembly. You will learn about WebAssembly Text, about the memory management in WebAssembly, about the stack machine in WebAssembly. You will see some Rust no-std code, no standard code. We will try some unsafe code with WebAssembly and Rust. And of course, we will also do a little bit of safe programming. So that will be the topic of today's talk. It will take approximately an hour, plus minus, depending on the number of questions that you have. We will see how we progress, and if I'm taking too much time, then please let me know. Please stop me if I'm too deep into some topics. Okay, very good. So I thought a little bit about what the general topic should be, the general example should be of my talk, and so I came up with the idea, one of the things that I'm currently spending a lot of time with, Advent of Code. I guess many of you know Advent of Code, and I hope many of you even do Advent of Code in any programming language. You can do it in Rust, you can do it in C#, you can do it in Python, you can do it in whatever you want. I really enjoy it, and you see I'm currently up to date. I have all my stars, and I thought it would be nice to take a look at the first day of this year's Advent of Code and use it as the basic example for my talk today. So what we are going to do, we are going to implement various variants of Advent of Code day 1, star 1, in WebAssembly Text, in unsafe Rust, in safe Rust, and we will see what that will teach us, okay? So if you don't know Advent of Code, let me quickly introduce it. It's a daily programming puzzle. You get it at, I think, midnight Eastern US time. So here in Germany and Austria, it is 6 o'clock in the morning. That means that every day since the 1st December, I stood up at, I don't know, 6:15, and at 6 I sat at the computer and worked on this example. And every day you get a nice puzzle packaged up in a super nice story about Santa Claus. Essentially, you have to help Santa Claus, or you are Santa Claus, and you have to find out the solutions of the puzzles in order to save Christmas. That's essentially the story. Now, I will not tell you the story of the first day. You can read it on your own. I will just tell you what the puzzle is, what we have to do today. So I would like to show you the input on which we have to work. This is the input on which we have to work. And the first example is traditionally a very simple one. The longer the Advent goes, the harder the puzzles are. So first day, first star is the easiest one that you can make. And in this case, we have the Christmas elves, and they are carrying some food. And as you can see here, we have the calories per food item, and we have 2 \n separating the different elves. So the first elf is gathering 3 pieces of food, and they are in total 6,000 calories, okay? These are in total 6,000 calories. The second elf only has 1 item of food with 4,000 calories. The next elf has 11,000 calories. The next elf has 24,000 calories, as you can see here, and the last elf has 10,000 calories. And the idea is that in our first day exercise, we have to sum up the calories of each elf and then find out which elf is currently carrying the most calories, and that will be our solution that we are looking for. And as you can see, the solution for our test input will be 24,000. Okay? Of course, we can also get the real input. That will be the real input. That is a lot more, but that we are not really interested in. We don't want to really solve it. The example, it's just a programming example that is kind of not trivial for WebAssembly, but also not too complicated. Okay, so this is our goal. We have to come up with a solution that calculates this one and gets us our first star of Advent of Code. That's the idea. Okay, good. Let's get right into it. The first level that I would like to do together with you is let's write this example purely in WebAssembly. Of course, we could now fire up a binary editor and type in some hex or binary numbers, but this is not really useful for us humans. We are used to type in text, and luckily there is a format for working with WebAssembly which is called WebAssembly Text. WAT. And this is our first goal. Let's write a simple version of our Advent of Code puzzle in WebAssembly Text. Pure WebAssembly. No additional language on top. No C, no C++, no Rust, no nothing. Just WebAssembly. Let's try that, and while we are looking at the solution, I will tell you a little bit about how WebAssembly really works at the very lowest level, and then I will tell you a little bit about how the tooling work, and let's see where we get here. Just a word of warning, I will not write all the code manually. I will lead you all through all the steps, but I will copy in quite some pieces of code, otherwise we would sit here until tomorrow. So I hope that's okay for you. So let's create a small file. Let's call it AOC1 for day 1, and let's call it WAT. That's WebAssembly Text. Now, the simplest WebAssembly module that you can build is that one. That is the simplest module of all. It's just an empty module. It doesn't contain memory, it doesn't contain functions, it doesn't contain any exports, it's just an empty module. But this is how you write in WebAssembly. Now, we have to open here or use the braces, as you can see here, and now we can start to write a little bit of what. Let's do that. Let's create a function. We use the function keyword for that, and then say, let's create a ping function. In the ping function, We can, for instance, get in a parameter. It looks like that. Then we can give it a name, a symbolic name. Symbolic names always start with a $sign here. And then we can give it a type, okay? The ping function should be very simple. It gets an integer 32 and it returns the same integer 32. Very, very simple to get started, okay? So we say I32. And then we can continue here inside the braces here. And the ping function should just return the result, which is an I32. And now comes the important part of how WebAssembly really works. WebAssembly is a stack machine. So in WebAssembly, everything is built on the stack. So you do not return something with a return keyword in WebAssembly. What you have to do, if you want to perform any operation in WebAssembly, or in our case, just return a value, you have to put the value that you would like to return on the stack. And therefore, we say local.get. This is the method with which we can take the input parameter $in and push it on the stack. And because we don't have any additional method after the after the local get, the result on the stack, the one item which is on the stack, will probably be the return value of our $ping. That is essentially one of the simplest functions that you could build. Now we can take this function and export it to external applications. And I just copied in the export statement. It says export the function ping, as you can see it here, and the export should be called ping. So if we now write a little bit of JavaScript code, or we use wasmtime in order to write a Rust host, we'll take a look at that a little bit later on, then the Rust host or the JavaScript code or whoever is hosting this WebAssembly module can call the ping function. Okay? So this is very, very simple. You might ask yourself, hey, what's this local get all about? And how should I learn how to write with this WebAssembly text and what the details are? Let me show you the greatest resources for learning how to write with pure WebAssembly. First, you can, of course, read the WebAssembly course specification. You can do that if you are into that. Feel free to do that. I read large parts of it, but I didn't really read every single word of it because at the end of the day, in real life, I'm going to use Rust. But still, it is an interesting read. Even more interesting is the MDN part, the Mozilla Developer Network part, where you can read in the WebAssembly homepage about the fundamental concepts. And here you can see some information about WebAssembly text format. This is exactly what we are currently working on. And then here on the right-hand side, you see it, you also have the instruction reference. And if we take a look at the variable instructions, you, for instance, see here get local, and then you always see here directly in a playground what you can do with that. And in this case, you see you have the local get, you have the local set, and so on. So this MDN is a great source for learning WebAssembly text, and WebAssembly text is a great source to really, really understand what's going on behind the scenes. So as Rust developers, we have a little bit of a heart for the low-level stuff, right? And the lowest level that you can go in WebAssembly is WebAssembly text. So I think if you want to learn a lot about WebAssembly and you use it a lot, you should maybe spend a few hours, you're currently doing that, learning the fundamentals so you really understand what's going on behind the scenes, okay? So let's quickly take our app here and compile this app into a real WebAssembly module, right? And for me, the tool that I always use here is Just. I don't know if you know Just. Just is a command runner, similar to, let's say, Make or something like this. Just is really, really useful. You create just such a Just file, and inside of the Just file, you can simply put some commands, and they are very simple to call. And in this case, you see, I'm using a tool from the WebAssembly binary toolkit, the WABIT, and this WebAssembly binary toolkit has a tool which is called what2wasm. So it just takes the WebAssembly text file and creates a WebAssembly module out of it. This will give us the Wasm file. I don't need that one, and we will need it in a second, okay? So let's run just build. And that will execute it, and you see, voila, here is our WebAssembly file. If we take a look at this WebAssembly file, and I can switch my editor, this one, then you will see that here we have the WebAssembly file. Here you have the method ping in it, and you see it's just a few bytes of code. So this Wasm file just is, I don't know, 38 bytes long. I think that is quite okay. This is what we just created here, okay? So you see, we can easily use this WAT file in order to write meaningful software. Now, the next step is that I'm going to paste in a bunch of lines of WAT code. This is exactly the code that I generated for you. And now I would like to walk you through this code, okay? And I will show you step by step what this code means and what we can do with it. And I would like to start with this method here, parse num. Now, what does this method parse num do? What it does is it takes from memory, we'll talk about memory in a second, a bunch of bytes, which are ASCII characters. This will be the input, just a bunch of ASCII characters. This will be the input. And if we are standing, for instance, in this input exactly here, then this method will parse the number until it finds \n or the end of the input. So in this case, if we run it here with index 0, the result will be 1000. If we start it here with index 1, 2, 3, 4, \n is 5, 6, then the return value will be 2000. I think you get the idea, right? And now let's take a look how we can do that in WebAssembly Text. In this case, we get an index inside of memory so that we know where in the input we currently are. Additionally, we get the length, the total length of the input. That would be the total length of this input as the second parameter. Now we can return multiple values from this function. That's a very interesting learning. As you can see, a function here in WebAssembly Text can return multiple values. Then, again something new, we can declare local variables which are local inside of the parse num function. So this is essentially a local variable living on the stack. Then, next thing, you can see WebAssembly Text supports loops. We can do a loop here and give this loop a symbolic name. Remember the $loop, we will come back to that. This loop method here iterates over the input starting with the index stored in $ix, as you can see it here, and it increments ix as long as it stands on a digit. Okay, as long as it stands on a 0, 1, 2, 3, and so on. When it reaches a \n, or when it reaches the end, the length that we see here, then it stops interpreting the thing as a number, and it will return. The first result will be the return value, so the identified value, and the second result value will be the new value of ix. So it will point to the first character in the input after the number that was just read. Okay, this is our idea here. And now we have to read a little bit and understand what these functions are all about. This is, if you understand that one, you have learned a lot about WebAssembly, because this is now how WebAssembly really works and what it means that WebAssembly is based on a stack machine. You have to read these statements from the inside out. So if you take a look at the brackets here, at the very lowest level, you can find this local get $ix. This local get $ix will put ix on the stack. It is a push of ix on the stack. The next thing is here, this load 8u. That means that this thing reads 8-bit, meaning a single byte from memory, to be more specific, from the address which is currently on the stack, and it will take this address, use this address to read a byte from memory. So this, these two things here, they say read a single byte from WebAssembly memory at the address that local.get puts on the stack. So local.get puts the address on the stack, load8_u unsigned reads this address from the stack, pops the address from the stack, and uses that to index into memory. That will give us the ASCII value of the current character. Understood? So if we have in memory 1000, then we have a \n, then we have 2000, and the index is currently 0, then the 0, the address, will be pushed on the stack, and load8 will use the index 0 to go into memory and load the byte, which is the 1 here, at this specified memory location. Okay? Now, the read data from the memory will again, you guessed it probably, will again be put on the stack. It will be pushed on the stack. So we end up, after this yellow part here, we end up with the ASCII value of the current character on the stack. Additionally, we place here a constant 10 on the stack. So we have now two values on the stack. The ASCII value of the current letter and the constant 10. And then we can apply, I will use a different color here, the next operation, not equal. And guess what not equal does? It consumes two elements from the stack, that is the ASCII value and the value 10, 10 is \n by the way, and compares these two things. If they are not equal, and E means not equal, it will push a 1 on the stack. If they are equal, it will push a 0 on the stack. Okay, so this line here will end up in a single value on the stack, a single i32 value on the stack, and if it's 0, it's equal, and if it's 1, it will be not equal because we are using the not equal operator here. Now let's take the next line here. This is again, we could again do the check here. Here we are just checking whether the index is not equal the length. So we check whether they have not reached the end. And again, we push something on the stack. So at the end, with red and green, we have two values on the stack. The first value, sorry, that was the wrong color. Let's use it in red. The first value on the stack means have a \n question mark. That will be the first value on the stack. The second value on the stack will be reached and question mark. And now we will, new color here, we will use the i32 AND operator, which you can guess it, pop both values from the stack. So it will pop these two values from the stack and check whether both are 1. If both are 1, then it will push a value of 1 on the stack. If they are not both 1, it will push the value of 0 on the stack. So you see, everything works on the stack. Every operation gets its parameter from the stack, pops the parameter from the stack, and pushes the result again on the stack. And a very important concept here of WebAssembly is that when WebAssembly text is compiled, the consistency of the stack is checked at compile time. So if you, for instance, try to call the AND function and WebAssembly text recognizes that it doesn't make sense because there will not be two elements on the stack, then you cannot compile your program. At least in most cases. Okay? Got it? By the way, we would not need to write the statements like this, nested in brackets and so on. But for us as humans, it's much easier if we format our WebAssembly text just in these brackets so that we can read the text a little bit. So, and not equal, load from this address, load not equal with a constant, not equal of index, not equal of len. So it's easier for us to read. We could also put one command after the other in a sequential list and use and keep track of the stack in our mind. But as humans, that is very, very hard to do. So therefore, people typically write code like that if they write WebAssembly text directly, as you can see it here. Now let's check out the rest of the method. Now that we know how it is to read, I think we can understand it pretty well. This if statement simply checks the result of the AND here. So if we are not at the \n and we are not at the end of the input, then we get the current value which we are parsing, multiply the value by 10, you see the formula here, and then we add the current digit which comes from memory, and we subtract the ASCII value of the character 0, which is 48, from it. And this loop here that we have here will simply shift the digit to the left and add the next digit. So if you have, let me see like that, if you have 1000 as a string, the first thing that it will give you is a 1, then it will calculate 1 times 10, which is 10, and add a 0, and that is 10. Then it will calculate 10 times 10, which is 100. Next will be a 0, which is 100, and so on and so on. And then we will have 1000 plus 0 is 1000, and then we will reach the \n, and therefore this is our result. So as you can see, this loop here, with this not equal, and this if statement, and this add and multiplication, is a very simple parse implementation without any error handling at all. We don't care about any error handling. Last but not least, we increment ix by adding 1 to ix, and then we branch to the loop. Branching to the loop means next loop iteration. This does not mean break. Don't get that wrong. It does not mean break the loop. It means branch to the loop. So this means jump up here and do it again. Okay? If we miss that branch here, the system would exit the loop. And at the end, we need to push 2 values on the stack. And that will be our return values. You see, here we have the result, here we have the result, and these are the 2 result values, num and ix. This is the parsed value, and this is the new index, the index after the parsed number. So this is, as I said, a very simple version of parsing a value in WebAssembly Text, and now you know what's going on behind the scenes in WebAssembly. Before we move on, I will take a sip of water and I give you a chance to ask any questions that you might have so far. It's not common. It's absolutely not common. You typically don't do it, but it's the same as if you would ask how common is it to write assembler code. It's not very common, but there are situations where you want to build the smallest possible thing, the fastest possible thing, and then you write WebAssembly text. That's the first thing. And the second thing is you absolutely have to be able to read WebAssembly in case of problems. So even if you use Rust, for instance, and you simply don't know what's going on, you know, with Rust or C or C++, you sometimes want to take a look at the assembler code because you might want to find out what's going on or why something is slow or what's happening or what's leading to a certain error. And then you have to at least be able to read a little bit of WebAssembly code. So that is more relevant than really writing this code. But by writing a little bit of this code, you gain a much better understanding of what's going on behind the scenes. Does this answer your question? Absolutely. This is exactly how it works. Thank you for pointing that out again. As I said, you always have to find the most inner braces here. So these 2 statements will be the first 2 statements which are executed if you write WebAssembly text like that. They will put the local variable on the stack and the constant on the stack. The next thing that will be executed, you can go 1 brace level up, will be that one, you see? Down here, we have the same. We have, this is, let's take this color. This is the first that will be executed. Then we have this one and that one. And then we have that one that will be executed. And at the end, the add statement will be executed. And once the add statement is done, the set statement will be executed. So follow the braces. That would be my my tip. And then you understand how the order is. In real life, what WebAssembly will do, it will not really generate, or what WebAssembly text will do, it will not really generate the commands in this order. What it will essentially do, let me show you that here. It will reorder the statements. So essentially, the code will look like that. First, we have that one. Then we have that one. See? Then, after that one, we will have that one. Here, and then we will have the sub statement, as you can see it here. And then it will take this one. I think by now you understand the principle, right? And then it will take that one. Here we are. Then it will take the multiplication, that one. And then it will take the addition, as you can see it here. So it will rearrange the statements. But if you take a look at the sequential code up here, yes, of course it works because of the stack. This one pushes something on the stack. This one pushes something on the stack. Sorry, this one pops one thing from the stack and pushes a value back on the stack. This one pushes something on the stack. This one pops two values from the stack and pushes the result on the stack. So reading this sequential code in WebAssembly, you always have to keep the structure of the stack in mind. And for us as humans, it's pretty hard to follow code like that. So you don't write it like that, but you write it, it's much better to write it like that. But if you want to read code that is auto-generated from WebAssembly, for instance, if you want to take a look at code that Rust generated, for instance, it will not have this nice structure. It will have the ugly structure that I just showed you. Okay, so it's a little bit harder to read, and you always have to keep in mind that things are pushed on the stack, popped from the stack, pushed to the stack, popped from the stack. Very nice questions. Thank you very much. Additional questions? Awesome. Awesome. So we can now parse a number. And with that, I think we should take a look at how we do the rest. The rest is done in the getMax function, as you can see it here. This getMax function only gets the length of the operation, as you can see it here. And then it returns the maximum value. Can you remember what we have to do? We have to sum up these values and we have to find the maximum calorie number, which will be 24,000. This will be the second last ELF that we return. And now I think I don't need to go through all the details because you have already learned what get does, what add does, how you read this code, what this or means and the equal means. I think by now you should be able to read this code. It's on GitHub. I will give you the link afterwards. You can take a look if you want to. But we have some things which we haven't seen so far. This is another interesting one. This one is a call to the parseNum function. So this one calls a subroutine, the subroutine which we took a look before, and simply calls it. And if we want to call the subroutine, first we have to push the parameters for the subroutine on the stack. Therefore, we get local parameters and they will push the value of the local parameter on the stack. Understood? Okay, that's the first thing. That's a call method here. Now, we have another call method here, which calls found value CB. CB stands for callback. What's that? Let's take a look. Now, that is another very interesting concept of WebAssembly, and that already touches a little bit in the area of Rust, because obviously from WebAssembly, we would like to sometimes call a function from the host. Now, the host could be the browser running JavaScript. The host could be Node.js running JavaScript, but the host could also be Rust running Rust. The host could be C# running .NET. And every host can provide functions. And these functions are imported in the WebAssembly module using the import statement. So this is an import where WebAssembly says the host will provide a function, which is called cb.foundValueCB. This is the name of the function with a namespace here at the beginning. And inside of this script, I will refer to this function as $foundValueCB. And WebAssembly is even type-safe, well, kind of type-safe, because here I can say what the parameter will be. Essentially, this is a kind of debugging function. So it will report back to the host whenever the system has found a single value. So it should result back 1,000, 2,000, 3,000, whenever it has found a value for debugging purposes, we will go back to the host, and this again could be JavaScript, Rust, or whatever, and tell the host, hey, I found something. And this is exactly how you call back to the host. And remember, this is now not like in assembler calling an ABI, an abstract binary interface with a C calling convention to some other language. This is really a native WebAssembly functionality. Being able to import functions from the host And I only show you one possibility here. There are other possibilities too, but I show you the simple one here. A possibility to import functions from the host is a core principle of WebAssembly. And here we are just calling back to the host. Now, the rest of the method is just a little bit of WebAssembly text. You can take a look at it. We have a loop again, and at the end we return the maximum value and we export the method. I think that's pretty obvious. If you want to take a look at the very details of the code, check it out in GitHub. The thing that I would like to spend a little bit more time on is this guy up here, because that will be super, super important when we switch to Rust in approximately 3 or 4 minutes, okay? That is memory. Rust in memory, or memory management in Rust does mean that, sorry, I said something wrong. Memory management in WebAssembly, not Rust, in WebAssembly works differently from memory management in traditional application programming, because WebAssembly cannot access the whole memory of the computer. WebAssembly code can only manipulate bits and bytes inside of WebAssembly memory. And this is exactly such a memory block. Here I'm declaring that I, as the WebAssembly module, am exporting a memory element which has a size of 64 kilobyte, I think. Just one segment, it's called. We just export one segment. That's enough for our purposes. This memory can grow, and you can define the minimum and the maximum and a lot of other things. And I encourage you to take a look at the documentation if you want to know the details. But for now, this is not relevant. It's just a sequential number of bits and bytes in a specially protected area in memory. And the important thing here is that this memory is accessible from within WebAssembly and also from within the host. So the host can write bytes into this memory, and then WebAssembly can read bytes from this memory. The WebAssembly module can write bytes into this memory, and the host can read memory from there. But the important thing is that this is just linear memory. There is, and listen closely now, this is important, there is no structured memory management. There is no alloc function where you can allocate 20 bytes. You simply don't have something like this. You have, in our case, 64K of bytes, and it's just 64,000 bytes, and that's it. Do you want to store a structured data structure there? You have to deal with it yourself. Do you want to store a UTF-8 string there? You have to deal with it on your own. Do you want to add an array of strings somewhat, or a list of strings? There is nothing like memory management here. No garbage collecting, no structured memory, no allocator, no deallocator, no concept of freeing memory. You simply have a bunch of bytes and you are on your own. So the host and WebAssembly have to agree on a certain memory layout. The host could write some bytes, a string for instance, and the WebAssembly module could make a mistake and interpret it as floats. Of course, that's possible because they don't share a common type system, at least not on the lowest level. On the lowest level, it's just a bunch of bytes. And if you need to allocate and free and maintain a linked list of free memory blocks and so on, you have to implement it on your own. It's not there in WebAssembly. So that is a crucial element of understanding in WebAssembly. Yes, exactly, and you will see that in a second. You will see that in a few more moments. In a few more moments, we'll take a look at two hosts, and I will show you what's going on there. Exactly this is why you need these array buffers and this uint8 array and all this stuff. This is exactly what we have there. Exactly. Please understand, WebAssembly runs within a sandbox. You hear that pretty often. And WebAssembly can't hurt your computer because it runs in a sandbox. You hear that pretty frequently, and you might have asked yourself, how is this done? I mean, this is called assembly, so it can't do anything to my computer. No, it can't. The only thing that WebAssembly can do is manipulate bits and bytes in exactly that piece of memory. Full stop. It simply can't do anything else, at least currently. It can call methods, that's true, but in terms of memory, that's the only memory where it can read and write data to. Is it memory safe, type safe, or something like this? Absolutely not. Not at all. It's just a bunch of bytes. Questions so far? Or do you want to take a look at the different ways of hosting and how they communicate? Before we do that, let's quickly compile this guy, just build. And then we end up with, again, a little bit of a Wasm file. And let's open it up again in a hex editor. See, we only have a bunch of bytes, not a lot of bytes. See, here you simply see the names of the exports. That will be just strings. But everything else is really a bunch of bytes. And if we take a look, we have just solved the Advent of Code Day 1 puzzle with exactly 248 bytes. That is pretty astonishing, right? Let's take a look what we can do with that. And for that, I'm going to bring on a second version of Visual Studio Code where I have the ready-made hosts, because it would be too much time to set up these projects by hand. And the first thing that we will take a look at is the Rust host, okay? This Rust host, as you can see here, is referring to wasmtime. You probably have heard about wasmtime. Wasmtime is a WebAssembly runtime. It allows you to do just-in-time compilation of WebAssembly code and run it. Typically, you simply call wasmtime in the console. Wasmtime, it simply runs, and you specify wasmtime, your Wasm module, and it simply runs. You have maybe tried that already. You print something on the console, you set up a web server, you always use wasmtime. But wasmtime is also a library. So you do not need to use the ready-made wasmtime executable, but you can write your own Rust application and use wasmtime to host WebAssembly modules inside of your own process. And this is exactly what we do here. Now let's take a look at the source file here. And as you can see, this is my input of the Advent of Code. This is just, as you can see, an array, a slice of bytes. So this is not a string. Please note that. This is not a string. It's really just some bytes, because I use the .s bytes here. Okay. Now let's take a look what we do in order to load our Wasm file and to run the Wasm file. Here, I'm going to use a bunch of things that wasmtime allows us. Please take a look at the wasmtime crate to know all the details. There is a lot to learn here. Essentially, what we have is this wasmtime engine. In the wasmtime engine, we can load a Wasm module. Then we can put this we can associate this module with a so-called store. The store will then, for instance, hold a reference to the callback functions. You see, this is a closure which we call found value CB. This is exactly the method that we were referring to here with this import statement. See it? So it's pretty simple to specify a function or a closure that can be called by a WebAssembly module. Then we instantiate the module and we put in the store where we have things like the callback functions and so on, the module, which is the WebAssembly file here, and some imports, see it here. Once we have this instance, we can ask this instance for the memory. So as the host, we now tell the WebAssembly module, where is your memory? So we are asking WebAssembly for a pointer to exactly that memory location here, see? So this is where we get this Wasm memory thing. And then, what can we do then? We can take this memory and ask for a mutable byte reference to exactly that memory location. And then I simply iterate over my bytes up here and copy them, as you can see it here, into the WebAssembly memory. So here, from the host side, I am filling the memory in my WebAssembly text in my WebAssembly module. Once I have that, I can call the getMax function, which is exactly the function that you see here. I simply call this function, and I call it with some type parameters because we pass in one integer 32. Remember, the one integer 32 was the length, this one. So let's take a look at the Rust file here. This is the length that we pass in, the input.len, see that one? And the result will also be an i32. So the result will be an i32, and that will be my max value. So the output will hopefully be a bunch of found values. and a result which should be 24,000, and that's it. So let's give that a try. So I have in my just file the run rs, which will build the WebAssembly text file into Wasm, then build my Rust host with cargo build, and then run everything with cargo run. So just run rs, run it, and come on, show me the result. I want to see the result. Give me the result. Good morning. The compiler takes a little bit of time, as we all know it and love it, right? Here it is. See? Bunch of found values. These found values are the callbacks triggered from WebAssembly into Rust. And down here we see the output, and you see the result was correctly returned back to my Rust host. Okay, got it? This is how you write a Rust host, and of course you can do a lot of stuff here. Provide more functionality, provide more callbacks, write more elaborate data structures into the Wasm memory, do whatever you want. But you have to understand that there is no, at least at that level that we are currently at, there is no common type system. WebAssembly has no idea what a Rust struct is. WebAssembly has no idea what a string is. WebAssembly has no idea what UTF-8 is. The only types that WebAssembly understand are a bunch of numeric values. Bunch of integer, bunch of floats, bunch of long vectors, bunch of bits. That's all it can handle. Nothing else on this level of WebAssembly. So if you ask yourself, hey, this WebAssembly is just like intermediate language from Java or from C#, absolutely not. Take a look at the Java intermediate language. Take a look at the C# intermediate language. Those intermediate languages are on a much higher abstraction level. They are object-oriented. They know structured data types. They know classes. They know polymorphism. They know interfaces. They know data types like structs and many, many other things. All these things are not there in WebAssembly. WebAssembly is very, very low level. It has a small instruction set, and therefore it's easy to compile into assembler at runtime, and therefore it's fast. Now let's take a look at a host in JavaScript just to show you the difference. In my case, I wrote the host in TypeScript. Now let's take a look at the package JSON here. And as you can see, I don't need wasmtime for that here because JavaScript, Node.js in particular, is capable of hosting WebAssembly directly. So if we leave Rust and enter JavaScript, we don't need wasmtime anymore because Node.js knows how to deal with WebAssembly. Now let's take a look at the TypeScript file here. This TypeScript file, first thing that it does, it reads, as you can see it here, with the fs package, it just reads the WebAssembly module. Now, setting up the callbacks is just an object where we use here this one, this property, as the namespace. Can you remember? Here we have the namespace here. Then we specify the function name, and then we simply do exactly what we had in Rust. Now we can instantiate the WebAssembly module, which is exactly this Wasm buffer. This is the Wasm file, as you can see it here. And we specify the callbacks. And those callbacks, they will end up in WebAssembly in this import here. So that will be the callback, right? Now, if I scroll down a little bit, we can say, hey, this WebAssembly module exports something. But here we lose type safety in TypeScript. Because here we are in any land and we have to manually specify the input parameter of getMax, the output parameter of getMax, and we have to specify that also memory is exported. Memory can be accessed by using the memory interface, which is built into JavaScript. So this is built-in functionality of JavaScript. Then we can take this memory and wrap an unsigned int 8, so a byte array, around this piece of memory. See? And then we can use the text encoder class, which is also built into JavaScript, and encode our string in UTF-8 bytes into the bytes which are now in this memory. So these two lines here, they take the string up here, and copy the bytes encoded in UTF-8 into this piece of memory. This is what this TypeScript code does exactly here. And then the rest is a piece of cake. Just call getMax and print the result. That's it. Want to give it a try? Oh, we definitely should. We definitely should. Just run JS and it's compiling time. And here we are. See, it works like a charm. The same WebAssembly module compiled from WebAssembly Text. And now we have this WebAssembly module and we host it in Rust and we host it in JavaScript and it works like a charm. Questions? I'll take a sip of water to give you a chance to ask questions. The callback function is in Rust. Here you see the callback function. The callback function simply takes the value which was recognized and uses the printline macro to print the debug output on the screen. So this callback function is here in Rust. But if we are taking a look at the TypeScript host, the callback function is suddenly TypeScript. So the WebAssembly host can, in his or her programming language, provide callbacks which WebAssembly can import and call. And with that, they can communicate. No.
We're just using Rust to interact with WebAssembly.
Exactly. I wanted to show you what's going on because now in the next step, when we compile Rust to WebAssembly, we have to understand that out of our Rust code needs to come something like that. This is what's going on behind the scenes. The Rust compiler is compiling Rust code not into assembler, but in something like that. Exactly like that. Use whatever you want. I played around with Wasm Edge. I played around with wasmtime. I played around with Wasm. Time is the thing that I like most. Maybe because I started with it and I have the most experience with it. The others are probably very great too. But I simply like wasmtime and I'm used to this library. Currently, we have the strange situation that we have multiple competing WebAssembly runtimes. And I guess that over time, there will some WebAssembly runtimes go away and we will only have a very few number of WebAssembly runtimes which are specialized on certain areas. But currently we have a lot of WebAssembly runtimes and it's quite hard to choose. Exactly. And wasmtime is not just available for Rust. If you have a C# application and you would like to host the WebAssembly module in C#, you can simply use the wasmtime NuGet package. And then you are the C# host. And you can load WebAssembly and you can execute it. And the callback function can be a C# function. By using wasmtime or any other WebAssembly host that you would like to use. Wasm Edge, Wasm, whatever you would like to use. Exactly. And with that, you have full control over the host. You can, for instance, limit the amount of memory that the WebAssembly module is allowed to use. You can limit the file access the WebAssembly module is allowed to access through WASI, which we will not talk about today, WebAssembly Systems Interface. So by building your own host, you have full control over what the WebAssembly module is allowed to do. Are you ready for the next step? I am. Yeah, question. Do we have a final question? And then we should maybe go on. Yeah, ask. Okay. There is a difference in speed. There is a difference in the number of supported WebAssembly standards or technical previews. Some of them are really powerful when it comes to ahead of time compilation. So you can take a Wasm module and, for instance, take Wasm Edge and compile it to machine language ahead of time. And with that, getting a pretty fast a really fast native compiled executable. They are also very different in their partnerships. For instance, Wasm Edge is partnering with Docker. So when you run WebAssembly modules in Docker, they will use Wasm Edge. So yes, there is a difference in functionality, in performance, in supported features. It's a little bit like browsers. Why does the world need multiple browsers? Well, the world would probably not need multiple browsers if the world would be an ideal place. But the world isn't an ideal place. So therefore, we have multiple browsers. And now we have multiple Wasm engines. Yeah, that's it. I'm sorry. Okay. Deal with it. Why would anybody build additional WebAssembly runtimes? Well, because we can. That's the only answer that I have for you. Yeah. Let's leave the area of WebAssembly text. Let's close this one down and think about how we could implement exactly that functionality in Rust. And for that, I would like to show you a sample implementation. A sample implementation that you could probably come up yourself if you have a little bit of Rust knowledge. See that one, right? This is the whole solution in a single line. It simply splits up the entire strings using \n, and then it takes all the different lines of every elf, parses it in I32, calculates the sum, calculates the mux, and that's the result. See? So that's it. We can now take this single line, compile it into WebAssembly, and we are done, right? Well, not right. It doesn't work like that, because we would need so much magic in that area. If we compile this into WebAssembly, a lot of incredible stuff will happen, and you will see that in a second. For instance, we learned that WebAssembly doesn't understand what a stir is. So if we compile this thing to WebAssembly, something strange must go on, because WebAssembly doesn't have a stir. Who deals with strings? WebAssembly doesn't have bounds checking for arrays. WebAssembly doesn't handle panics. So what if the unwrap leads to a panic? WebAssembly has no concept of a panic. So we cannot just take this thing and compile it and hope that it works. It will not produce any useful code. We have to go down to the metal, and this is what I would like to show you here. Let's try to think about the solution in Rust that is very similar to what we implemented in WebAssembly Text. What do we have to give up in order to solve something like that? First, all the functionality of the standard library, we don't want to have it, because the standard library is so huge and so functional rich, we simply don't need it. For our example, we don't need the standard library. We only do a little bit of byte manipulation, and that's it. First, no standard library, so we need no STD. Second, no panics. We have to get rid of panics, because the infrastructure that Rust brings with panic handling is huge. If we simply enable panicking and have a single unwrap somewhere in our code, the resulting WebAssembly code will be huge. We will not have 150 lines or so. We will have thousands and thousands of lines of WebAssembly code, just because we have the panic infrastructure. Same is true for bounds checking. We are accessing an array here, or a slice here, and if we have bounds checking, then all the code of bounds checking has to come in. If we do that, Rust will create a whole lot of WebAssembly code, which we don't want to have, because my explicit goal in this next step is to build a nearly efficient Rust logic that produces nearly the same WebAssembly code as the handcrafted WebAssembly text version. And let me introduce you to exactly that version here. This is what we can do in Rust in order to make it as small and tiny as possible. Well, here, first thing, the first thing is no standard. Okay, no standard library. Otherwise, thousands of lines of WebAssembly code imported. We don't want to have that. In order to have native pointers, we use the nosted compat crate, which gives us, for instance, null pointers outside of the standard library. Super useful. Then, no panicking. We want to remove the standard panic handling completely. If a panic happens, the code should run in an endless loop. That's fine for us. That's the simplest way of dealing with panics. Of course, we could add panic handling, no problem, but then we will end up with, again, thousands of lines of WebAssembly. And for now, just for the sake of it, I would like to try to get in Rust to something similar to what we've seen before. Now, this is an interesting one. This is at the very lowest level what we have seen in WebAssembly Text as the import statement. This here says, hey, Rust, somebody external will provide a callback function in the CB namespace. See, this is a macro which instructs the code generator that this will be a WebAssembly import statement, and we will be able to call this external function. This is not an external C or something like this. This will end up as an import statement in WebAssembly. And now you understand what this extern with this link stuff really means. It's just the import statement of WebAssembly. Now, where is our memory? Answer, there is no memory. To be more specific, Rust will add memory automatically. But what we can do is we can define static buffers in Rust, and Rust will place them automatically inside this linear memory. Okay, so here we are generating a static buffer of bytes, and Rust will automatically move the static number of bytes inside of WebAssembly memory. And now we can start to write code. The first ping method, like that, no mangle, just means that it should export this function as it is. It shouldn't inline this function and things like that. So that will be an exported function. The parse number function looks like that. See what I do here? Get unchecked. This is important. If I don't do the get unchecked here, Rust would immediately spit out a lot of code for bounce checking. But if we try to come as close to the fastest version that we can think of, we have to, unfortunately, enter unsafe land. I'm very sorry for that. And we have to get rid of bounce checking, because if we don't do bounce checking, it will be fast. This will end up in a single WebAssembly instruction, which will be the load statement, which you can probably remember from WebAssembly Text. It will load 8 bits from memory at the given index. Just to make sure that you really are, that we are on the same page. Can you remember this statement here? This one? In order to teach Rust that it should use exactly that WebAssembly functionality and not to bounce checking and a lot of other magic, we have to use the get unchecked. So that will be a single WebAssembly statement. That will be 3 WebAssembly statements, because it will push index on the stack, it will push len on the stack, and finally it will use the lower than operation, which will be similar to something like that. Get it? So I think you understand the principles. Let me show you how this looks like if we take a look at the just file here. Here you see I'm building exactly this application, but this time I'm building it for wasm32 unknown. See? And I'm compiling it to release. And afterwards, I use another binary tool from WebAssembly, which takes the WebAssembly module and converts it back into WebAssembly text. So what we do is we ask Rust to generate WebAssembly, and then we translate it back to WebAssembly text in order to be able to take a look at it. Let's give it a try. Just build. Okay, here we are. And now we can take a look here, and let's get rid of that one. Take a look at the WAT file. Nice. If I scroll down, 183 lines, right? And if we scroll up, this looks an awful lot like the code that we've written before. See the get max function? And we see this local set, and we see this const, and we see this branch if. It is a little bit differently structured, because the Rust code will be probably better than my code. I don't know. But at the end of the day, it has a similar length, as you can see it here. The code ends here at line 127. And if we take a look at the WAT file, here we had 114 lines. But here we don't have this nesting going on, but it has no braces. So I think you get the idea. So that sample should show you that if you get rid of the standard library, if you get rid of panicking, if you get rid of bounce checking and a lot of other things that Rust has built in, you can generate WebAssembly code which is near to what we can write in manual assembler code in WebAssembly text. That is the goal of this exercise. In the last thing, which we'll take a look in a few minutes, this will be then the last thing, and that will be the closing of my session today. In the last thing, we will take regular Rust code and compile that to WebAssembly, and then you will see the difference. And the difference is huge. But for now, we simply tried to make Rust code as efficient as possible in terms of WebAssembly. And that means getting rid of a lot of the security. Would you write Rust code like that? Probably not. But it's good to understand what's going on behind the scenes. One final thing, and then I'll take questions again, is the memory management again. See, here we have the memory. That will be the memory allocated by WebAssembly. But then, if you take a closer look for demo purposes, I have written here a get buffer functionality, which will just return a raw pointer to the buffer which we have up here. See? This will just verify that the size isn't larger than the size of the buffer. Here we allocate 1024 bytes. If it is larger, we return a null pointer. Otherwise, we simply return a raw pointer to this buffer. Now let's take a look what Rust does with this pointer. Let's take a look at the get buffer, and you will see that here it returns a very strange number. It returns 1,048,576. See that one? This is just a place inside of this memory here, and it is exactly down here, this data. See it? This is exactly this data region, and this data region is now a region filled with static data inside of our memory. Before this memory location, so address 0 until 1,048,575 will be memory that Rust is going to use. You know for what? For stack. This is not the stack of WebAssembly. This is memory that the Rust runtimes needs. That's interesting, right? So what we learn here is that the Rust runtime uses the memory provided by WebAssembly to put in its own memory model. Get the idea? So when Rust allocates memory, if we think of, for instance, we allocate a vector at runtime, it has to allocate this memory from exactly that WebAssembly memory, and it has to manage the memory itself. It cannot go to WebAssembly and say, hey, allocate so and so many bytes. WebAssembly is simply not capable of doing that. Rust has to manage the memory on its own. And even if you generate something like a static buffer up here, Rust has to somewhere find place for this buffer inside of WebAssembly memory. And this is exactly what's going on here. That is kind of amazing. Many people, when they approach WebAssembly, they think that WebAssembly is this powerful runtime, which works similarly to C# or Java runtime that has a memory management going on and things like that. But that is not the case. You simply get a flat number of bytes, and whatever is running in WebAssembly, you have to deal with it on your own. And therefore, Rust must bring its own memory management. There is no operating system too. We cannot go to an operating system and say, hey, I would like to allocate memory. We are in WebAssembly. We don't see the operating system. Questions before we move to the last demo? No, it has a multiple of 64K. So you can ask for as much memory as you want. I think 32-bit is currently the stable version. I think the 64-bit is... I'm not 100% sure what is stable and what is not stable, but you can have way more memory than just 64K. But I think it is a multiple of 64K, if I can remember correctly. No,
like this one,
no, you have a misunderstanding here. There is no concept of allocation. You simply, you have an address. The address starts at address 0. And allocating memory in terms of WebAssembly means that you simply decide to use address, I don't know, 42,679 and put something there. And you have to remember it on your own, that it is there. You cannot ask WebAssembly for allocating memory. You simply use an address. That's it. Maybe it helps like that. Let me show you that. Are you familiar with this function here? Std slice from raw parts. From raw parts takes a raw pointer. The pointer is an address. It's just a number, okay? It's an address. And in this case, a length. So this from raw parts says, I simply decide that at this address, this number of bytes is from now on a slice of bytes. And then I interpret this slice of bytes as an UTF-8 string. So what you can do in WebAssembly, if you write Rust code for WebAssembly, you can simply decide now, without allocating any memory, you can simply say, hey, I want to create a vector out of nothing. And I simply decide this vector starts on byte 0 and it has a length of 32. That's it. And then you simply interpret the bytes which are already on address 0 for the next 32 bytes, and you interpret them as a vector. That's your decision.
Okay. So this linear.
It's complete linear bytes, and you have to remember on your own where your data is. And if you would like to reallocate something, for instance, if the vector has to move inside memory, WebAssembly does not help you at all. You simply have to find on your own a new address from which you know that you don't overwrite someone else's data. Well, only inside of your WebAssembly module. Yes, absolutely. So your WebAssembly module can read and write any byte inside of its own memory, and it's responsible for its own bytes. But what it can't, and that is the important one, it can never ever access anything outside of its own memory, or even access memory from a different WebAssembly module. So it's like a container, you know what I mean? So it cannot break out of the module, but inside of the module, it's chaos. You have linear memory and you have to deal with it on your own. Do whatever you want in that area. Yeah. This is strange, right? But these are the things that you only learn once you play with WebAssembly on a lower level. Because then you understand what WebAssembly can do and what WebAssembly can't do. I have a suggestion. Let's do the last demo, and then we'll spend the rest of the time just for asking and discussing. Is that okay? Let's try that, because I think the last demo will be interesting for you. The last demo, here I just took this example here. It's exactly that example here. And again, I wrote an execution in JavaScript in this case. This is exactly the same again. But this time, I am going to run the full version of the Rust implementation. Now the problem that we have, forget Wasm bindgen, this will be the last step. The problem that we have is that this function here, day1 part 1, requires an stir. JavaScript doesn't know what a stir is. JavaScript has no idea what a stir is. So somehow we have to create a Rust stir in order to call this method. But JavaScript has to allocate memory, which will be treated as a stir later on. So if we just use Rust's built-in mechanism without any magic coming from Wasm bindgen, which I will show you in a second, what we have to provide is we have to provide our own alloc and free functions written in Rust. So what we have to do is we have to allocate memory manually in Rust. So here the allocate function simply says allocate a certain number of bytes, because we are allocating a vector with a certain capacity. And then we are taking the raw pointer to this memory. This will now be part of the Wasm memory, where JavaScript can also write into the code. So the code is allocated in Rust, but it lives in WebAssembly memory, and therefore we can write into the same code that was allocated in Rust, we can write to it from JavaScript. And then we tell Rust that it should forget about this allocated memory, so it will no longer be part of the borrowing and ownership concept, so it will not free this memory anymore. And then we simply return this pointer. So in JavaScript, we can go on and say alloc the number of bytes that we need for this stuff here. That will essentially give us an address inside of our WebAssembly memory. Then in JavaScript, we can wrap around this piece of JavaScript memory an unsigned int array. We can encode the string into this thing, and then we can call the raw version of this function. Now the raw version of this function, again, takes the raw pointer and creates the slice from it, and then uses the str from UTF-8 in order to check whether it's correct UTF-8 data, and only then it will call the real functionality here in Rust. And at the end, we will need to manually free the buffer again. Now this freeing of the buffer here goes into our free method. Here we are simply rebuilding the vector from the pointer which we got from alloc, and then we call drop in order to free this memory. But it's not freed from a WebAssembly standpoint because the memory is still there. We simply free it from the viewpoint of Rust. So it's pretty complicated to run this stuff and to execute this thing. Let me show you that it really works. If we now, by the way, this is no longer no standard, right? This is traditional handling of panics and all this stuff. So here I have the just file, and I will call it just build plain. It will compile everything, and let me show you the difference. Here we have release, and here I have the WAT file. And let me show you the difference. Before we had 138 lines. I will stop for nobody. I will stop for nobody. We stop for nobody. 15,206 lines of WebAssembly text code for the same task. That's the difference. And that is not using Wasm bindgen. That is just Rust with the standard library, with panic handling, with all the security features that Rust has. The difference, which is approximately 15,000 statements in WebAssembly, the difference is the runtime of Rust. Do you see the difference? I mean, take a look at this Wasm file here. I can show it to you. Let me open it up in the Explorer. Here it is. It has 1.7 megs. Okay, we can make it smaller by removing a lot of stuff, and we can run a bunch of optimizers on it, and then it will be a few hundred kilobytes. But still, it is hugely different from what we had before. I'm not saying that you should write now WebAssembly text, and I'm not saying that you should always use nested programming because we also don't do it in assembler. But I wanted to show you the difference, how large the necessary task is that Rust has to bring to the table in order to use WebAssembly with the full security and safety and functionality of Rust as compared to what WebAssembly can do out of the box. Now, if we take a look, 5 minutes and we're done. If we take a look at all this stuff, do you really want to have to write this method? Do you really want to have to write this method, free and alloc? Do you really want to have to write this raw wrapper around your method, taking the pointer, having to reconstruct everything? What I really want to do is I really want to just pass in a JavaScript string, and I want it to be done. And now this is exactly what Wasm bindgen does. Wasm bindgen is a crate that you can reference, and then on top of the method, here you see it, you can simply use the macro Wasm bindgen. And then you don't use a cargo build in order to build this stuff, but what you do is you use Wasm pack to build this stuff. Let me show you what's going on. Just build WB, here it is. And what you will end up with is a package folder. See, you will also get a WebAssembly file, but you will get much more. You will also get a bunch of JavaScript. Let me show you what this JavaScript is all about. It contains the single function, and that is what we want to call, right? It even gives us a TypeScript code where we see that this is a string and it returns a number. And if we want to host this thing and run this thing, we can simply say, see that, single line, call it, pass in the string, and we don't need to deal with anything of that. But behind the scenes, Wasm bindgen is doing all the heavy lifting that I was showing you for the last 1.5 hours nearly. WebAssembly, the Wasm pack and the Wasm bindgen is having all these functionality, like calling the malloc. Now, what is this malloc? malloc is a function which comes out of WebAssembly. It's called __w_bindgen malloc. This is exactly similar to what we have built manually when we were responsible on our own. No, which was? I'm lost. Overview from full RS, which when we were responsible on our own and we implemented the alloc function on our own. But the point is here, we don't need to do it on our own because wasmBindGen generates exactly that for us. But behind the scenes, the alloc function is there. And if we pass in a string, it will use this alloc function in order to alloc the necessary amount of bytes. It will use the encoder, here you see it, to copy everything into this memory location. So at the end of the day, we now have this pointer, you see? And then it will call the real Rust function. And it will pass in the pointer exactly as we did it before. So this is what's going on behind the scenes. So it's not magic. This WebAssembly bindgen is just a code generator. And I mean, it's getting even crazier. If we take a look at this this package file here, and if we take a look at the WAT file, we are now at 12,000 lines. You might ask yourself, why is this now less code with wasmBindGen than without wasmBindGen? That's very simple, because wasmpack will execute a bunch of optimizations on top of WebAssembly to make the whole thing a little bit smaller. But without the optimization, it would even be larger than the 15,000 lines. But still, do you see the difference? There is a huge difference. And this is exactly what I wanted to show you today. I wanted to show you what WebAssembly can do out of the box and what WebAssembly can't do out of the box. How much we have to sacrifice in order to make Rust produce as efficient WebAssembly code as we could write it manually with WebAssembly Text. Of course, this is not relevant for everyday programming. We love the security of Rust. We love the functionality of Rust. And therefore, we simply accept that the generated code from Rust in WebAssembly will be larger. Because Rust has to introduce all these things to WebAssembly because they are not there. That is what the assembly part in WebAssembly means. It's simple. It doesn't have a lot of capabilities. It's near to assembler code. And finally, I've shown you that even if you don't sacrifice any of these things, you still have to do a lot of pointer magic in order to communicate between JavaScript and Rust. And this is exactly where wasmBindGen comes in. It generates for you the necessary JavaScript code, the necessary TypeScript code, so you do not have to deal with translating strings from JavaScript to Rust, translating structs from JavaScript to Rust or the other way around, and many other things. So that was a long talk. It took me a little bit longer than 1 hour. It took me 1.5 hours, but I still hope that it was interesting for you. I would like to take the opportunity to say thank you. Thank you for being so patient and listening to me. And now I would like to open it up for Q&A.